Oh. All right. Anybody else have any trouble logging in this morning? They they did send us an email over the weekend that said that they were heightening the security on Zoom, and that it was going to mean that we had to make sure that we logged in through the utexas.zoom.us, which I forgot to do. And they also said that they were going to be setting up passwords on the meetings, and I looked yesterday to figure out exactly what that meant, and it didn't seem to say that we needed a password, but I can't tell if that's going to affect you guys. I see 45 participants, which is fewer than we've had in the previous meetings, so I'm going to guess some people are having trouble logging in too. Let me take a quick look at my work email. Oh, no complaints yet. All right, well, you know what? This is part of why we record these things. We'll go through our regular class, and I'll put it up on YouTube when we're done. People who are having trouble logging in, I hope that they'll be able to get the YouTube links to work later. Apart from the technology, how's everybody doing today? Did you have a good weekend? Everybody's still healthy, I hope. All right, doing good, that's good to see. All right. How about on the current homework? Now, I did tell you guys that I only knew that you'd be able to handle the first 6 or so questions, but if you looked a little further into the list of questions, that they do take you through the end of chapter 5 and then into chapter 6. So I want to start working on those things today. And in particular, I wanted to start today with a triple integral. I did have some people writing to me over the weekend about one of the homework questions that asks you to compute an integral over a certain 3-dimensional shape. And I thought, well, we could probably start with that one if you guys would like. Unless you have another example that you want to try, can I take the one from the homework? Let's have a look at, it seems kind of dark in here today.
Could we look at number 7?
Okay, I don't remember what that question was. Let me see if I could pull that up. Do you remember, Brianna, right offhand? Do you have it in front of you?
It's it uses cylindrical coordinates, and it's in between, like below a cone and within a cylinder.
I want to avoid cylindrical coordinates just yet because we haven't talked about different coordinate systems. So I'm glad you asked, and we will probably be able to do that one before we quit today, but I wanted to do one that's still in rectangular coordinates. So the one that somebody was asking me about, I think, is problem number 9 on the homework set. Let me see if I've got that one right here. I'm pulling up the quest homework. Well, anyway, you know what? I think I do remember it from memory anyway. Let me pull this down. I have this figured out. But... All right, so here was the problem, is they asked you to integrate some function. I don't remember exactly the formula. It was something like z plus 8x. To do an integral over a 3-dimensional shape. So there's going to be some mention of volumes involved in there. That's too bright. do I make it less dim? Yeah, let's try that. This was an integral to be computed over a certain set S, which was a figure in three-dimensional space, and I'm going to try to draw it even as I describe it with formulas. So it was bounded, first of all, by the parabola y equals x squared in the xy plane. Let's label the axes. So here's the parabola y equals x squared. And that equation describes a curve in the plane, or thinking about this as an equation in three variables, it can be, well, one equation in three unknowns would describe 3 minus 1 is 2, a surface in three-dimensional space. It's this surface where you stretch this thing out along the z axis. Okay, and then in a similar way, one of the other defining equations is y equals x. That's another edge to this region. You think of that as the line in the xy plane, but of course I can let z be arbitrary in that equation. So I stretch it in the direction of the z-axis and I get this plane. And then the third equation, the third part of the boundary was the z equals x. That's a line in the xz plane, or I can stretch it. It's funny perspective on it. Let's draw it a little higher. If I now stretch it in the direction of the y-axis, then you would see another plane coming through. And that one will describe the top of this region S. So focus for a second just on these three surfaces. There's the parabolic, sort of a bent sheet of paper, and then there's a plane here, y equals x, and another plane here, x equals z. And I can show you the three-dimensional shape that's bounded by those in a fresh picture. So that'll look like this. Let's see, here's the axes. And then on the bottom, you have the region that's bounded by the parabola and the straight line. So that stretches from the points 0, 0, well, actually 0, 0, 0 to 1, 1, 0. So those are 2 points in the xy plane, but those are the 2 points where these curves meet. If you want y equals x squared and at the same time y equals x, that's two equations and two unknowns. They intersect in just zero-dimensional sets, which are just individual points. And the two solutions are these two, 0, 0 and 1, 1. And then on top of that, you want to draw this plane where the z-coordinate will rise as high as the x-coordinate. So at the bottom, that plane is already, the roof of the figure that I'm trying to make is already going to be all the way down at the bottom. But over here, at the point 1, 1, or above the point 1, 1, 0, if you allow z to be as large as x, the x-coordinate here is 1, and so I'll go up a distance of 1 to get to the point 1, 1, 1. And then from here, I draw a figure that's lying over this parabola, but rising up off the bottom plane. And likewise, there's this straight line on the floor, which will lie under a straight line that rises from the origin to the point 1, 1, 1. So you're seeing a kind of a swoopy shape. It's a three-dimensional shape. It's got this parabolic wall on one side, but the roof slants down from a height of 1, coming all the way down to the origin. So sorry for the lousy artwork. It's actually represented a little better, perhaps in the picture that accompanies the problem in the homework set. But I want you to have something to stare at, because I want you to emphasize with you guys how you can set up the limits of integration in a Fubini's theorem kind of problem. This original problem is going to ask us to do a computation and compute an integral over this three-dimensional shape. And conceptually, there's nothing hard to do here. Like every integral, this asks you to take the set S, shown here, split it up into a bunch of smaller pieces, pick a point at random inside each one of those pieces, And at each one of those points, evaluate the function shown here, and then multiply that by the size of your piece. Now, size in the three-dimensional setting means volume. So this funny little three-dimensional shape, you need to imagine that being built together by a bunch of boxes all piled on top of each other, sort of a Minecraft shape. And you multiply the sizes of each one of those, the volumes of each one of those, by the value of this function somewhere inside each one of these little sets. So that's the principle, and we can even estimate the value of this integral. Obviously, if I go piece by piece, every time I evaluate the function, I'm going to be picking a point somewhere inside this region, and I'll be evaluating this function. Well, at every single point in this set, the z-coordinates are positive, and so are the x-coordinates. I mean, I'm above the xy plane, so the z-coordinate is positive, and I'm on this side of the yz plane, so the x-coordinate is positive. So obviously the value of the function is positive everywhere. On the other hand, the z-coordinates are always less than or equal to 1. That's the highest point. And the x-coordinates are less than or equal to 1 as well, because this is the single point that's furthest out in the direction of the x-axis. So if z is at most 1 and x is at most 1, then the value of the function is at most 9. And so the values of the function everywhere are going to vary between 0 and 9. On the other hand, the total volume of this figure I can estimate too. One way to do it would be to say, oh, well, if I simply raise the roof here at the low end so that it's as high as the height is here at the high end, then I would be getting a kind of a box. Oops, sorry, I didn't mean to. It would be a box that touches here at the current highest height, but it raises the height in the back. So I would get a figure that now looks like this. It's got that region that's between a parabola and a straight line on both the top and the bottom, but now it's of uniform height. And so the volume of this region here would be less than the volume of the box that surrounds it. And the volume of this one would be equal to its area on the bottom times the height. And the height is 1. And the area on the bottom, I could calculate that with an integral, or I could estimate it. Let's see, well, the length of that line segment is the square root of 2. And I don't know, this variation here, maybe I should figure out, but hang on. Let's get the area on the bottom real fast. The area on the bottom is the area that in the xy plane that's between the graph of y equals x squared and y equals x. And you know how to compute that from your previous calculus courses. That would be the integral as x goes from 0 to 1 of x minus x squared, which should be x squared over 2 minus x cubed over 3. And that's 1/2 minus 1/3, which is 1/6. So I get the volume of this box to be a total of 1/6, which means that the volume of this region is less than or equal to 1/6, and it's clearly positive. And so when you compute the integral of this function f, right here, over this set S, that's going to be less than or equal to the product of the maximum value of the function and the maximum possible value of the volume. So that's, what would that be, 3/2? All right, so I've got an estimate for the value of this integral. It's going to be something that's clearly greater than or equal to 0, but less than or equal to 1/2. And just to eyeball it, I would say maybe we've got about half of the total volume that's in here. And furthermore, the values of this function are, there's only a single point where they rise as high as 9. Usually they're much lower than 9. So from my point of view, I expect the value of this integral to be, not a very big fraction of this, not even half as big as this. I might expect something on the order of 0.2 for the value of my integral. Now, having made an estimate, let's think of how we would actually calculate this with Fubini's theorem. Fubini's idea is you're going to, when you break this thing up into little boxes, you'll be multiplying the values of the function at a point in each one of the boxes times the size, now meaning volume, of that little box. And the way you get the volume of a box is by multiplying together the dimensions of the box. There's a small increment in the x direction, there's a small increment in the y direction, and a small increment in the z direction. So from Fubini's point of view, the way we should rewrite this integral is to say, okay, we're going to evaluate this function and multiply by the volume of a little box, and then sum over all x's, sum over all y's, and sum over all z's.
Dr. Rusin?
Yes, go ahead.
Wasn't the original function z plus 8x?
Maybe. I didn't pull up the integral, the homework question, so this will have to just be an illustration. I couldn't even guarantee that each one of you guys would have the same function, so.
No, well, I'm just saying is that from what you were working with when you started this whole.
You mean my original?
Yeah.
Maybe. Z plus 8x. Yeah, z plus 8x. Oh, here. Yeah, you're right. Thank you. Good call. All right. So, we still have to figure out the limits of integration on each one of these three integrals, and I'll come back to that in just a second. But I'm setting you guys up for the idea of different coordinate systems. Because in order to get something that looks like Fubini's theorem, we keep reminding ourselves that we're summing over all these little boxes where we're multiplying the volume of the piece times the value of the function. The value of the function is the same formula that I've been using. But when you're using rectangular coordinates, and when you make the decision to split the set S up into a bunch of boxes that are all piled on top of each other in line with the x, y, and z coordinates, then the volume of a little piece is calculated by multiplying a small variation in each of the three different axes together. I know that sounds kind of obvious, but if you get used to saying it that way, then it'll make it easy for us to start doing those problems in cylindrical coordinates that she asked about earlier, and polar coordinates and spherical coordinates and so on. So see that when you write down this triple integral, focus on saying that you're summing, these are elongated s's, you're summing values of the function times small amounts of volume. All right, now let's get back into the Fubini routine of trying to figure out the limits of integration. And here again, I want you to remember some of the things we learned from doing two-dimensional integrals. One is that you can rewrite this as a triple integral with the three variables in any order. And second is that I gave you a set of words to ask yourself about talking to points and asking them their coordinates. I'm going to use that way of thinking again, that line of questioning to set up my limits of integration. So the first thing I want to do is change the order of the variables from the way that I wrote it here. In a three-variable problem, you have six possible permutations of those three variables. I know from experience when doing problems like this particular one, it makes more sense to put the variable z on the inside, and then x and y, they can go in either order actually on the outside of that, but it's going to be easier for us to have y next and then x to follow. And if you're going to ask me how did I know in which order to put these, let me just say, I think I said it last time too, you could try all the 6 permutations and see which one feels easier for you. Or start doing a lot of these problems and pick some more from the book. And the more you do, the more, I don't know, feel that you get for the good order of integration. So let's just accept for a moment that this is the best order of integration and figure out how we're going to get the limits. When you're writing down the limits, you go from the outside in. So I'm going to start by figuring out the limits of integration on x. So for that, you need to ask yourself, what are the least and the greatest values of the x-coordinate that you see anywhere in this three-dimensional set? So I don't know how well you can actually visualize this three-dimensional set, but start talking to all of these points and ask them about their x-coordinate. Their x-coordinate measures their distance from the YZ plane. So the minimum value of the x-coordinate would be the x-coordinate of the point that's closest to the YZ plane, and the largest x-coordinate would be the x-coordinate of the point that's furthest from the YZ plane. It seems pretty clear to me that the one that's closest to the XY plane would be this point here, which is the origin, and the one that's furthest would be this point here, although there is a tie. You could go for this one up here if you like. After you've stared at the point, you actually need to get its x-coordinate, which usually you do by getting all three of its coordinates, x, y, and z. And so we have to ask ourselves for three pieces of information about the point that we're staring at, so that we'll have three equations to write down, and we can solve the three equations for the three coordinates. So like this point here that's at the top, the way that I would represent that one is it's at the intersection of the plane that determined the top of this figure, and that was the plane where the x and z coordinates are equal. Furthermore, it's on the vertical face over here on the right of the picture, and that vertical plane came from having equal x and y coordinates. And finally, it's also on the curvy left-hand surface. The left-hand surface came from saying that we erected a wall above the parabola y equals x squared. So here's three things that I know about my point, which turns into three equations about the point, and three equations I can solve for the three unknowns. Basically, the three coordinates have to be equal, and the y coordinate has to be the same as the square of the x coordinate. That forces x and y to be either 0 and 0 or 1 and 1. We talked about that earlier. In our case, the point that we have right here is the one that has x, y, and z all equal to 1, which gives me the coordinates shown. All right, you already kind of knew the coordinates of this point. I'm making too big of a deal of it, but I wanted you guys I want to force you guys to keep thinking about just getting the coordinates of the points by writing down a sufficient number of equations and then solving them. Okay, to get my next limits of integration, I have to say I'm going to pass inside these square brackets, and as I do that, I'm going to start holding x constant. Well, holding x constant means you're only going to be looking at the points that have a fixed x coordinate. If you look at all the points in the x, y, z space that have a fixed x coordinate, that makes a plane that's perpendicular to the x-axis. This is the set of points that have x equal to some fixed x coordinate. Last week I was using the letter C just to say I'm holding it constant. It'd be easier for you, I think, algebraically, if you just get used to saying, I'm just going to call it x, but remember that x is constant. Now, you have to look at the three-dimensional shape and intersect it with that plane. So you have to visualize the set of points that you're going to get in this figure when you hold your x-coordinate fixed. So let me try to chop this three-dimensional shape perpendicular to the x-axis to get the range of values for that coordinate. So here's what I see now. I'll draw it kind of lightly. There's the coordinate axes, but now I'm going to draw another plane parallel to the YZ plane that's intersecting my shape. So down on the floor, there was this line segment that intersects my plane in just one point. There was also this parabola that intersects my plane just in one point. Then that vertical wall in the three-dimensional figure becomes a vertical wall in this plane. Likewise, this vertical wall becomes a vertical line. And as far as the other two parts, the other boundary portions of my three-dimensional figure, there's the floor, that's the xy plane, which when you intersect it with this plane where x is constant, that turns into a line segment. That's the set of points where y is equal to 0 now. And finally, there was the other plane that said I was supposed to look only at points that had x and z coordinates equal. Well, if you've held the x-coordinate constant, that means you're also holding the z-coordinate constant. So that's what I get when I intersect this three-dimensional shape with a set of points where the x-coordinate is held constant. You're going to get a rectangle. It's a rectangle bind in the, let's see, I can keep track of all the points in this figure, which doesn't look like much of a rectangle. I just should have drawn this a little differently there. Sorry for the bad perspective. That line segment should have been drawn parallel to that one. Anyway, I can keep track of where I am in this plane using the y and the z coordinates only, because the x coordinate is already held constant. And in terms of y and z, that bottom edge is y equals 0. The vertical line over here has arbitrary z coordinates, but the y coordinates are determined by the y coordinate of this point. And that point lay on the line where x and y coordinates are equal. So the equation of this vertical line is now z equals, it's now y equals x, where I'm thinking of x as being a constant. That's why this is just a single line. Likewise, over here, this is another vertical line, y equals a constant, but what constant is it? It's the constant x squared. And finally, this top line, this horizontal line, that's a set of points where z is a constant. And if z is a constant, what constant is it? Well, it's the constant value x, because that was the plane, that was the equation of the plane that was determining the top edge of my figure. So you'll notice that I'm writing the exact same equations that I had before that gave me the boundary of my three-dimensional shape. Only in the previous setting, these equations were describing surfaces. Now they're describing lines where y or z coordinates are being held constant. Only the name of the constant is something that involves x, and that is a constant because I'm holding x constant in this figure. So now I can describe the limits of integration that I need on y, and z will come immediately as well. Just within this figure now. So that's the set of points in my original 3D shape that happen to have this fixed value of the x-coordinate. Within this figure, I need to write down the least and the greatest values of the y-coordinate. I get my smallest y-coordinate by going as far to the left as I can. Remember where the y-axis points? So my smallest I'm sorry, I missed
z equals 0.
This should have been z equals 0. I'm so sorry. Yes, that should have been z equals 0. Okay, so my smallest y-coordinate would be the y-coordinate of a point that's as far as possible in that direction, and that would be any of these points. And my greatest y-coordinate would be the y-coordinate of a point that's the furthest in that direction, and again we have a tie, it would be any of these points. So you could stare at this point, for example. That was a point that lay on the floor. That was a point that had a z-coordinate of 0. It was also a point on that straight line where y is equal to x. And finally, it was a point that had x equal to that fixed x-coordinate. And as I said, today I'm not using the letter c anymore. You can still use it if it makes it helpful for you. We were holding x constant in this entire plane. So that would give me my 3 coordinates. You can then use it to solve, I have 3 equations linking the 3 coordinates. You can use those 3 equations to solve for the coordinates. X is whatever this constant value is, y has got to be the same, z is equal to 0. And in particular, the one that I want right at this moment is the y-coordinate of this point, but that's this number c. It's the current value of the x-coordinate. That was the greatest value of the y-coordinate. The lowest y-coordinate would be the y-coordinate of a point like this, which is again on the floor. This time it's on the parabola, and it's all, like everything else, taking place in this plane where x-coordinates are held constant. Well, there's your 3 equations. Solve them and get your 3 coordinates. X is whatever the current x value is, y is the square of that, and z is 0. And this was the coordinate that we're looking for to put right here. So, again, to emphasize what I did, I held the outer variable fixed. I stared at all of the points in my original set that had that fixed value of that coordinate, and then I scanned all of the points in the set looking for the minimum and maximum values of this coordinate. If I can go one more step inward, now I'll hold y constant as well, and I'll ask for the minimum and maximum values of the z coordinate, which might depend on the values of x and y that I've held constant. So let's see, when you want to hold y constant, you're intersecting with a plane that's perpendicular to the y-axis. That means intersecting this previous plane with a plane that chops, I don't know if it helps you for me to move my hand, but the intersection with the previous plane will now just be a single line. These are all the points that have x equal to a constant and y equal to some other constant. Maybe I should call it d. And so all that I have left now is a single line segment. And I need to talk to the points in that line segment, asking them for their minimum, asking them about their z coordinates. And I want to know the minimum and maximum values of the z coordinates. Again, you know which way the z-axis points. So the minimum z coordinate would be the z coordinate of this point. The maximum z coordinate would be this point's z coordinate. And you already can see I've labeled it. The minimum z coordinate is 0. The maximum z coordinate is x. X is a constant as we have moved inside here. It could have been, you might have seen something that involved y's in here as well, because once you pass inside the curly braces, then the variable y has also been held constant. So whatever formula involving x's and y's shows up in there, that would be my new limit of integration. So that's the long process that you go through after you made the decision to evaluate this integral in Cartesian coordinates using Fubini's theorem. Here's your little measure of how volume is computed in Cartesian coordinates. And then Fubini says to write it as a triple integral with your limits of integration calculated in the way that I've just shown you. All of that being said, now it's going to be 3 Calc 1 type integrals to compute. Let me do them in stages for you. The outer one and the middle one I won't change right away. But inside the braces, what I'm going to do, write the dy and the dx. Inside the braces, I'll compute this integral with respect to z by finding an antiderivative with respect to z. And then plugging in these two values of z. Z equals 0 is easy. Z equals x is not so hard either. So I'll get an integral, a double integral now, where my function of x and y is going to be, it looks like x squared over 2 plus 8x squared. And now I evaluate the inner integral by finding an antiderivative with respect to y and substituting in these two values of y. Since this is a constant, this has no y's in it, the antiderivative with respect to y is just that constant times y. And when I stick in these two values of y and subtract, I'll just be, well, I'm actually multiplying by the length of this interval in the y-axis. Let me pause here for a second. Kyle, you have your hand up?
Yes, Professor, could you explain the 9 times 1/6 part above? I don't really understand it.
Over here?
Yeah.
That was me doing what I encouraged you guys to do before you dive into all these calculations. I always encourage you guys to estimate the value of your integral before you start. And one of the ways to estimate it is, since you're going to be multiplying values of the function times the sizes of the pieces, if the value of the function is, in our case, less than or equal to 9, then multiplying values times the size of the pieces won't give me anything bigger than 9 times the sum of the sizes of the pieces. But if you add the sizes of the pieces, what you're going to get is the size of the whole shebang, the size of the set S. Size in our case meaning volume. So if you know that the values of the function are all less than 9 and the volume of the shape is less than 1/6, then the value of the integral can't be any bigger than 9 times 1/6. So That's my explanation as to why I got this inequality. Of course, I'm banking on you believing me when I give you these inequalities. Is this where your question really lies?
Yes, I understand where the 9 came from, but where's the 1.6 come from?
Oh, that was my estimate of the volume of this thing is that it looks to me like this shape fits inside this box. So the volume of the shape is less than the volume of this box. A volume of a box is easier to get if it has a constant height. In our case, the height is the height of this dot, which is 1. Then the volume would be the area on the top and bottom multiplied by the height. So I just had to figure out the area of that figure that's on the top and the bottom, which I did over here as a Calc 1 kind of problem. That's where I got the 1.
Okay.
All right, we're almost to the point of checking to see if our estimate is good. I think I was advocating a number much smaller than 1.5 as the integral. Let's see how we're doing here. To integrate this function with respect to y, since that's a constant, I'm just going to, by the way, half an x squared plus 8x squared adds up to 8.5 x squareds. And I'm going to multiply that by y and evaluate at these two values of y, so I will just get the difference between those two values of y. And finally, I went from 3 variables to 2 to now just 1. This is an integral that I know I can compute. This integral, if I can pull out the 8.5, this is now just an integral as x goes from 0 to 1 of x cubed minus x to the 4th, which I can integrate easily. That's x to the 4th over 4, which when I evaluate at those endpoints will give me 1/4, minus x to the 5 over 5. And again, at those two endpoints, everything is very easy. So I get, that's actually 1/20th. I get 17 halves times 1/20th. It's 4 1/4 divided by 10. I get 0.425. It's a little bigger than I estimated. I think I said, when I wrote this down, I think I gave some rationale as to why I was expecting an answer in the range of about 0.2 or 0.3. I got a little bigger than that, but I'd go with it. I didn't get a negative number. I didn't get something that was more than 1.5. In fact, I didn't even get something that's really close to 1.5. So certainly my answer is inside this range. And I guess I'd believe it. All right, I'm not so concerned about the arithmetic. Of course, I want you guys to do it right, but I do want to stress a couple of things that we did in this example. I wanted you to see that the part of the description of an integral that asks you to compute the volume of each one of your pieces, it's represented by this triple of little differentials. That's the one thing. And the second thing that I want you to see is the process by which I got these limits of integration on the 3 variables by successively holding more and more of these variables, these coordinates fixed, and then asking for the range of values on the next one of the 3 coordinates. If you keep that stuff in mind, then it becomes possible for you to work in other coordinate systems besides Cartesian coordinates. And this is what we're going to be doing in chapter 6. The book begins chapter 6 by talking about transformations, and I will get to that, but probably not till, well, certainly not until tomorrow. But I want to illustrate the process by which we're going to do this with an integration problem in polar coordinates. And I want you to observe that I'm using the same wording that I went through, the same process that I went through here in Cartesian coordinates. So let me do an example like that. Let's find an area. I'll tell you what, let's find exactly the area of exactly the same region that we just went through, a region in the XY plane, the region that's bounded by the parabola and this straight line. And I really already know what the area is, but I want to show you how you would set up this area calculation by writing things in polar coordinates. First of all, in polar coordinates, you would write this this figure in a different way, this line, for instance, yes, I can describe it by saying what happens to its x and y coordinates, but I can also say what happens, how I describe it in terms of polar coordinates. This is the set of points where the theta coordinate is exactly equal to pi over 4, just a straight ray coming out of the origin. This one is a little harder to do in polar coordinates, but it's not impossible for us because we can rewrite x and y in polar coordinates. The left side is r sine of theta, the right side is r cosine of theta squared, and if you multiply this out and divide both sides by r, you can actually solve for r. R turns out to be sine of theta divided by cosine squared of theta. So here is a polar description of exactly that same curve. This is a curve given explicitly in polar coordinates. I'm telling you the r coordinate in terms of the theta. Now, how should we take this region and compute an integral over this region? So for example, to compute the area, you would get the area by splitting this shape into smaller sets and then multiplying the number 1 times the area of each one of them. You add those all up, you'll just get the total area of the whole set. In Cartesian coordinates, the natural way to split this up is with a bunch of little boxes that are lined up in line with the coordinate axes. In polar coordinates, a similar decision would say, why don't you take the whole region and split it up into smaller sets in which the r and the theta coordinates are varying. So in other words, I've got all possible values of theta from 0 to pi over 4 in here. If I draw a few of those rays, and then I draw some of, so these are sets of points where theta is held constant. In the same way, I can draw the regions where r stays constant. So here's r, well, I guess you know this point that's furthest away, this has got a distance from the origin that's equal to square root of 2. And here's r being equal to some other values, r1, r2, and so on. If I draw both sets of curves, that splits up my original region into these little slices. And a very natural thing to do now is to compute the area of the whole region by, well, I'll write the same symbols before as I did before, computing the integral this way. What this means is to...
Could you slide up your paper a little bit?
Yep, certainly. Thank you. So I split the set S into the smaller regions. I go to each one of these regions. I evaluate this function. I keep getting a 1. And I multiply the value of the function by the area of this piece, or any of the other pieces. And then I add all those up, and that'll give me the total area. Here's the thing that's a little different between what we did in Cartesian coordinates and what we're doing now, is at the next step, I'd like to actually start computing something by using Fubini's theorem. And Fubini's got the same idea. He says, yeah, to keep evaluating your function, multiply that by the area of one of your little chunks. Well, your little chunk stretches across a range of thetas. This little arc here represents a range of thetas. This particular one, the theta goes from C1 up to pi over 4. And in this same region, I've just let R range over a little range of values, all the R's between that number R2 and that number R3. But you don't get the area of this region by simply multiplying the length of that arc times the length, you don't multiply the length of that line segment by the range of thetas that's involved. Because as you can see in this figure, if I take exactly the same amount of variation in the R coordinate and exactly the same amount of variation in the theta coordinate, I get a new region over here that's clearly larger than that one. And in fact, it's not hard to do a little geometry and figure out what the area of this sector of a portion of a sector of the circle is. It turns out not to just be the product of the dr and the d theta, but rather you multiply the length of this line segment by the length of this line segment, which unfortunately isn't just d theta, but rather it's r times d theta times dr. The actual length of this segment, to get the length of the segment, you need to know not just the range of thetas involved, but how big of a circle are you measuring an arc on. You look at the current radius of your circle, whether it's this radius or this radius, and you multiply that radius by the amount of thetas involved, and that will give you the length of this little arc. And if you multiply the length of that arc by the length of that line segment, you'll get, well, actually you get the length of something that's a little different from the sector that I've indicated. But when we start taking our limits, letting the r's and thetas, the dr's and the d thetas get smaller and smaller, there won't really be a difference worth worrying about between the area of this region and the area of the slightly larger region that follows this, this line of constant thetas. So Fubini's idea in this case is, hey, take the set S, split it up this way, and then when you need to sum over all the different d thetas and sum over all the drs, you end up writing your area integral as an integral with respect to thetas and r's. The catch is there's an extra factor of an r in here. And this r is, well, first of all, it's something that a lot of you are going to forget. Don't forget it because you'll get the wrong answers. But it's intrinsically involved in exactly how you compute areas in polar coordinates. Now, our job in the rest of chapter 6 is going to be having to figure out a replacement for this fudge factor of an r when you switch to different coordinate systems. That's where we're going to have to get into this idea of transformations. Setting that aside, just for right now, just for today, I'm only going to deal with polar coordinates, and just trust me now or understand where this r comes from. That's the fudge factor that has to do with the changes of the areas. The other part of Fubini's theorem says, hey, well, you can do the integral as an iteration of two one-dimensional integrals in either order, but you've got to get the right limits of integration. And again, since I know from experience that when your limiting curves are given explicitly in polar coordinates, then it makes sense to have the thetas on the outside and the r's on the inside. Then this will be the way my double integral will be written. The range of thetas in this particular diagram is pretty easy to see. It's, you want to scan the whole set, talk to all the points in here about their r and theta coordinates. What goes down here will be the minimum theta coordinate that you find anywhere in the set. And you know the theta coordinate measures how far you've swung in this direction. You get your minimal theta coordinate by going to your clockwise most point anywhere in the set. And as you talk to these points in here, you'll see that you're getting more and more clockwise. You're approaching 3 o'clock as you get closer and closer to the origin. And in fact, you can find points that have theta coordinates as low as theta equals 0. Your maximum theta coordinate will come by going counterclockwise as far as you can. All of these points are tied for having the largest theta coordinate, and that their theta coordinate is pi over 4. So those are the constants that go in for your outer limit of integration. To get the range of values on your inner limits on your inner integrating variable, you need to hold the outer coordinate fixed and then ask for the minimum and maximum values of this variable, not on the whole set, but just on the set of points where that coordinate has been held constant. So go to one of these rays where theta is held constant and talk to me about the minimum and maximum values for r. The minimum value of r occurs for the points that are closest to the origin, and in our case, we can hit the origin. And the maximum value of r occurs for the points that are furthest from the origin. I need this guy's r coordinate. Well, to get it, describe this point as being the intersection of two curves. It's the set of points where theta is constant, and it's on the set of points where r is equal to that funny expression that I had before. So now you have two equations in the two unknowns, r and theta. Take those two equations and solve for r and theta until you know the r coordinate of this point. And obviously it says right here, the value of r expressed as a function of theta. So it's r's and thetas now, not x's and y's, but it's the same process of holding some coordinates fixed and looking at the range of values in the other coordinates.
Dr. Rusing, would you mind sliding up the paper just a little bit?
Yes, sorry, I keep forgetting to do that.
It's all good. Thank you.
All right, I am out of time, but as it turns out, this is an easy enough problem for you to finish if you wanted to go through it. The integral with respect to r will be r squared over 2. Plug in your endpoints, you'll get some function of theta. It's a little complicated, but actually it's just a trig integral, exactly like you had in Calc 1. So I would leave it to you to calculate a number. We already know the area turns out to be 1/6, so finish it if you wish. That's not the critical thing. The critical thing, two critical things. Make sure you know how to get the limits of integration. Even though it's polar coordinates, it's the same set of words where you're talking to points holding some coordinates fixed. That's step number one. The other thing that's important here is realizing that when you want to get the area of a little region, when that region has been found by slicing this way, emphasizing the polar coordinate system, then there's a fudge factor that shows up. Tomorrow, what we're going to do, Wednesday, what we'll do is figure out why that fudge factor is there by thinking of this in the context of even more general coordinate systems. All right, took me a little longer today, but that's complicated stuff. You can start trying the problems that do talk about coordinate systems. Read through the first couple of sections of chapter 6 and bring me some questions on Wednesday, and we'll start from there. Okay? Final questions you need to ask? All right, good. I'll see you guys on Wednesday then.